Okay, our next speaker is Zoran, and we know him from the Engage program, and he does like cutting edge stuff, and I'm sure this will be very good.
Thanks for that introduction, Greg. Okay, so I have 15 minutes. How many of you have heard me speak last time when I was here? Oh, well, sorry. I'm going to skip most of the stuff I talked about. It looks like only 1/4 of you have. But I want to tell you about some of the most recent stuff that I'm most excited about, just to give you a sense of what I'm striving towards, both from the perspective of my center at University of Washington and the nonprofit that's trying to provide a service to all the content providers and assessment entities, is that I think it's possible to take any classroom with any kinds of students, with any teacher, anywhere, and to reach 95% of sort of proficiency and mastery on any given topic. Now, of course, if you look at this number, this is sort of crazy talk across the board. Hopefully, within 15 minutes, I can show you that it may not be so crazy. The key thing that I've been working on towards, and I'm so glad that now it's making it into a title of conferences, is I've always been focusing on the fact that research, development, schools, practitioners, we all think that there's like a secret little thing that if we just did it, everything will be right. But in reality, it's really the entire system. That it's a very complex engineering system that you cannot ignore variables in, because if you do, you will sort of, all your outcomes will not be very valuable at scale. And so this is kind of what I've been thinking of, is really trying to do this kind of optimization, where I'm optimizing both aspects of the student, teacher, curriculum, and what happens at school, at home, such that together I get the outcomes that I'm actually trying to achieve. And how am I trying to do this? Well, there are 4 things here that I think they really need to be completely changed in order to be in order to be able to optimize this kind of ecosystem. First, the curriculum needs to be a very different thing. It's even when it is digital, it is rarely as variable and as morphable as it possibly can be. So as a result, what we're trying to do is take any curriculum and turn it into an infinite variation of itself. Now, as I'll mention, we're doing this on a fairly large scale that soon will be available to millions of kids. Second, instead of just looking at adaptation, or in my term, what I think of it as an optimization of just a computer and a person, that's not enough. First of all, it's not enough to just consider their mastery. You need to consider their sort of metacognitive skills, their self-belief in themselves, their persistence. All these other things end up mattering. But second of all, it's not in just the person. You need to consider the classroom, the peers, the teachers. How can you vary and optimize what the teacher is doing, what the classroom is doing, such that you maximize the effectiveness of the entire system? Finally, you can optimize everything about the classroom, but you still don't know necessarily what is the best modality of the blended organization of the classroom that would be most productive towards benefits to all kids. We all talk about blended classroom is good, you should subdivide things into units, but there's so many variables there, and nobody really has a clue. I mean, everybody talks in these general terms. It's best to pair kids up. But what does it mean? There's many different ways you can pair kids up, and nobody really knows what's the best way to do it for every topic, for every socioeconomic situation that you're trying to address it. So that's what we were really trying to do here. Let me just give you some insight into what I mean by sort of these different things. So infinite curriculum, if you sort of think about when everybody talks about an activity, maybe you have sort of an assessment that sends you back into the module to start it again, or maybe you can have it branched. But still, all you're doing based on the assessment is going back into the module that the assessment, or in its psychometric way, has determined that you don't know something. But the key thing is that you really need much finer grain ways of intervening here than to looking at the same module again. So let's take something procedural, like comparing two sort of numbers, or something more conceptual, where you have to sort of apply a set of rules in order to figure out what kind of combination of exploration will lead you to an answer, or something that requires you to have both reading comprehension and understanding and modeling from text in order to create the appropriate model of what is mathematically represented here, such that you can, from that model, then reason about how to solve that equation. So in this case, you see an example of one of our interventions where the kids actually build a model of what actually happens in the text prior to actually forming the equations on them. And if you look at any one of these entities, you start having sort of these maps. They're this large. And I just want to show you something. If you look at one of those problems, and you look at jump math or Singapore math, how they're actually breaking down the content on any one of those things, you get maps like this. So each one of those nodes is a type of problem. The edges basically depict the sequence or progression that the curriculum chose to go through for these problems. And you can basically see that even though these are highly acclaimed curricula, they don't agree. You know, there's some nodes that are only covering one curriculum and not the other. But perhaps the bigger issue is that if you look at the entire space, these two, and by the way, I should point out, if I zoom into this node, each one of these little buckets is hundreds of problems with exactly this in the same equivalence class in terms of conceptual difficulty. So if you look at what these two curriculum are doing, they're covering the space of these big circles. So you can basically see that this is created by people who really know how to design curriculum, but they're not covering even 1/5 of the space of all possible things just for that particular concept. So this is the state of most of the curriculum and the way in which it's presented to students right now. What we need is something much more systematic that is capable to actually understand the entire space and then see how the data of how kids learn actually allow us to figure out progressions through that particular space. I can tell you that this kind of construction, to our surprise, ended up being relevant not just for content providers, but also for assessment. Our nonprofit NLearn now has 3 different contracts with assessment companies that basically tries to create this massive, large-scale sort of breakdown of the concepts and exactly the detailed ways in which they depend on each other. So let me just show you quickly one of the things that is not under NDA, so I can actually show you. So this is solving linear systems, okay? The entire map of all concepts and how they're related to each other is in this particular. So let's say I'm going to zoom in here somewhere. All right, so this is one equivalence class of the types of problems. You see 2 equations. You need to solve them together. If I click on it, I can actually see in this bucket the 7 problems that are equivalent in terms of exact thought processes that kids need to go in order to solve them. If I click on any one of these, you will see that I'm seeing the right solution and I'm seeing distractors. So in this case, these are, I don't know how many, 6 different wrong answers that map exactly the ways in which kids that are thinking have some particular misconception, this is the answers that they would have. So if I click on any one of those, then this is the actual explanation. In this case, it says always make the first value negative. So this is a particular misconception with the kids when they're actually solving these equations, when they need to do 4x plus x, they actually always go with a minus 3x. If we go into some other one, for example, this misconception has 2 different ways in which you can be thinking wrong to get that misconception. One of them is never move the variable to the left-hand side, and the other one is never count 1 as a coefficient. When you have x plus 3x, you don't actually count x as 1x plus 3x. So you can basically see another interesting thing. If I hover over each one of these edges, it tells me how this problem is connected to some other problem in a way in which I only vary one dimension of variability. So in this case, I highlighted this edge, and it basically tells me that the previous problem did not have to move the variable terms to the left-hand side while the next one did. And so I have sort of now deep understanding of how each one of these problems is slightly simpler or slightly more difficult with respect to something else, which leads me to have these progressions. Now, what's interesting here, this graph is very large, is because it subsumes combining like terms and many other prerequisites to solving linear equations. All of these things are actually embedded in this space. If I wanted to look at only linear equation-related top-level terms, I could actually have a different slice of this of space, which is going to be a lot more control. So in this case, these are only the variables that relate to substituting terms into without any prerequisites. So what's interesting is that this entire space is automatically generated from encoding the thinking processes student needs to go to solve all possible linear systems of equations. And this wasn't possible until maybe 2 years ago when we published the first paper in this space. So here's another thing we can do. Can somebody tell me what Juanita is doing wrong by solving these problems? Well, I only have 4 minutes. You don't have time. So it turns out that she does the right thing when they're the same number of digits, but when they're not, she just adds the single digits together. And so any kind of assessment entity would just say, well, she successfully solves these problems with this percentage, right? But and so you would have some item-based response thing. But here, what we can do is we can figure out exactly what she's thinking, and this is what she's thinking. And because she's thinking that, it means that she actually has a problem with place value as opposed to actually addition. She does all the additions exactly right. She just doesn't understand what to do when there's no 10-digit numbers. And this allows us to have much deeper insight into what kids are thinking and what are the missing pieces. Another point is that this maps now to ELA as well. So we're able to actually map the space just like we did for math on the entire English language. We're now doing this for Voyager Sopris, which is the 5th largest supplemental material provider in the United States. They have 500,000 students per grade. We're doing 6 grades of ELA and 6 grades of math, including reading comprehension, which is broken down into thought processes and how kids should be thinking. So I'm really excited about that. You heard about XSTEP already, 200 million learners. The NLearn platform is providing ways in which to sort of parameterize and vary every particular content that they're providing on their platform, such that every one of these can be brought to its optimal performance. So for example, what we're able to do is develop thinking processes towards reading comprehension text, including how the kids should be thinking, what are the best problem-solving strategies, how to use generalization, summation, inference, and multiple interpretations, all on semi-automatically generated content. So instead of having only some number of passages, there are passages or sections of passages automatically constructed specifically for kid learning inference between sentences. Of course, we're doing persistence. For example, in India, this is the most fundamental thing. All of these kids are first-generation learners, which means they don't have anybody in their family who's ever went to school. Those kids don't understand what their abilities are, what they're actually capable of doing. And that development is perhaps more important than the actual content that is trying to be covered. Another thing I mentioned is once this infinite curriculum is created, what you can do is now apply state-of-the-art reinforcement learning onto figuring out what to do next. And here I want to point out something that I always do, which is which I think is very important. If you do psychometrics to analyze what the kid does and doesn't understand, all you do is bin them in a particular category of what they do and do not know. We're not doing that. We're trying to figure out what is the next action that will enable the kid to learn the most from what they are now. And the key thing I want to point out is that that's a very different question you're asking. And as a result, you have a very different optimization process that leads. So we're always asking, what is the best next learning step? Not just for the kid, but for the teacher, for the parent, or for the peer. So here's an example of what these algorithms are doing. This is fraction learning. 0 is random ordering of sequences of set of things that kids need to learn. The key thing I want to point out is that expert progression is worse than random ordering of these concepts. Okay? This is not because these people are very smart. I'm not trying to. The key thing is they ignored some of the variables that ended up being important because of the way in which you simply have to do it to make it tractable for when people are doing things. If you don't do that, you can see a whole bunch of different automatic algorithms that figure out which parameters are best performing. There are many other things that we're optimizing in this ecosystem. So for example, what are the optimal hinting strategies? What are the optimal ways to develop persistence and tenacity? Long-term effects on domains like self-identification, what are the teacher in-classroom activities. For example, we can figure out what can the teacher do for the last 10 minutes of the classroom based on the current state of all of their kids. Okay? Similarly, what are the best ways to organize the classroom such that to promote the best maximal learning of the entire group of students? So, okay, so this is all talk. What did we actually do at scale? So we tried to ask a question, can we get kids to solve these kinds of equations after just an hour and a half of learning, even in the elementary school, including first grade? So this is 7th grade material. It takes about 5 to 6 weeks to nominally cover. Of course, many people don't end up covering. We did this in Washington State. We did it in Norway, where kids solve almost 8 million equations. And these are the outcomes that we get. Any classroom that did hour and a half participation in this wing-long challenge, this is the percentage of kids that reached mastery. The only statistically insignificant thing is the kindergarten. There were only 3 kindergartners that wanted to learn algebra, so ignore that part. But this is 95%. This is possible if you optimize the entire learning ecosystem, in this case for the state or a country, for a week-long period towards a particular goal. And so, as I was saying, it's not just the student, but the teacher, curriculum, and everything else together. So just to tell you the last bit of things, so we did a trial, same teacher, exactly the same curriculum, but we're varying the NLearn platform and the standard way of delivering this. We wanted to see what are the effects that this platform can do if we remove the variable of a teacher and we say we don't know how good or bad the curriculum is, it's going to be the same no matter what. Okay, so here are some interesting teacher effects. Number of times the students are assisted in the classroom, and this is a trial over 12 weeks. This is the entire semester trial. So the same teacher helps students almost twice as many times in the same amount of time. So it's as if you added one more teacher for the entire semester. If you look at sort of how much time they're spending in assisting students, it's, again, similarly, twice as much. If you look at who they're helping, you also see that there's much less focus on kids that are sort of more or less, teachers have kind of given up on the bottom end of the class or on the high end. Here, because the NLearn platform actually enables the teacher to help kids on the entire spectrum. Similarly, how many times does the teacher pivot? What we mean by that is teacher realizes that they haven't taught something well, goes back and tries to describe it in a different way. In the NLearn platform, you see that some teachers actually do it 2 to 3 times per classroom, whereas they don't do it at all on paper. Okay? So this is where we lose kids, and this is the thing that ends up happening. So in terms of kids, number of problems solved is 4 times more for the same amount of time. So everybody knows time on task is important. Time on task here is the same. For the same amount of time, kids did 4 times more work. That's what's actually possible under this kind of platform. And so similarly, of course, the correctness, kids actually did 10% better, despite the fact that teachers tended to give a platform to their weaker class, and they worked on paper on the stronger classroom. So that's my key point, is that so much is possible, both in terms of empowering inspired learning by an individual and by looking at the entire ecosystem and how much you can change it. We're not talking about percentages. We're talking about factors of improvement over the entire process. And that's what makes me excited when I wake up in the morning and try to make a difference. Thank you.